Stars, how are they formed, live, and die? Hello dear friends who are passionate about space and science. In this video, as you can understand from the title, we will talk about stars. Astronomical celestial bodies capable of carrying out the fusion of elements in their cores thanks to their enormous gravitational force are called stars. For us humans, observing this formation is impossible because a star completes its formation in about 10 million years on average. This means it is very slow compared to the human lifespan. So how does a star form? Stars begin to form through the gravitational collapse of astronomical gas and dust clouds, called nebulae, which contain mostly hydrogen, helium, and heavier elements, due to the gravitational force resulting from a comet or supernova. Gas clouds collapsing, meeting the criteria of Jeans instability, first turn into a flat disk by rotating, and over time, they continue to rotate faster, pulling matter towards the center, forming a hot and dense core. For this to occur, the gravitational force must exceed the total magnetic, thermal, and rotational energy. As a result, the first core that emerges is called a protostar or primitive star. The forming protostar continues to heat up due to the effect of gravity, and when the core temperature reaches 99 million degrees, hydrogen atoms undergo fusion, producing helium and very high energy. After millions of years, when a sufficient amount of mass collapses into the core, a flow burst occurs in the protostar, and star formation is completed. The mass of a star during its formation also determines its lifespan. If a star forms with a very large mass due to the influence of large mass gas and dust clouds, its lifespan is not very long. Because they cannot bear this load, a phenomenon called a supernova explosion occurs, and they disappear. Stars with longer lifespans have relatively less mass. However, the mass does not continuously collapse until it reaches the center. Nuclear reactions occurring at the center compress the gas in the environment, increasing the pressure. The outer mass wants to collapse inward due to gravitational force, but this cannot happen due to the gas pressure at the center, and equilibrium is established. The balance resulting from the struggle between the two forces is called hydrostatic equilibrium. In massive stars, the balance is disrupted when the rapid nuclear reactions in the core deplete the hydrogen fuels. With the decrease in central pressure, the outer mass collapses inward. As a result of this collapse, the star turns into a white dwarf. However, stars with more than 8 to 15 times the mass of the Sun cannot withstand the pressure of the collapsing mass at the center, and a large explosion, namely a supernova, occurs. If the mass of the exploding star is 10 to 60 times that of the Sun, a black hole forms. For example, Eta Carinae, located about 8,000 light-years away from us, has about 150 times more mass than the Sun. This means it emits about 4 million times more energy than the Sun. However, while the Sun has been emitting energy for about 4.5 billion years and is expected to emit for billions of years more, Eta Carinae has only existed for a few million years. According to astronomers, this star is expected to undergo a supernova explosion at any moment. But there's not much to fear. Considering that there are approximately 200 sextillion stars in the universe, we can say that these explosions are quite ordinary for us. To understand the number of stars more easily, we can also say that if we count all the grains of sand on Earth, it would average about 7.5 sextillion. Dear science lover, don't forget to subscribe to our channel and like the video to be informed about more videos. How big are stars compared to Earth? Starting with the Sun, which illuminates and heats our Earth, it is 109 times larger in diameter than Earth and has a mass 330,000 times greater. The smallest known star so far, EBLM J0555-57 is located 600 light-years away, with a diameter 59,000 kilometers larger than Earth's but smaller than Saturn's. Its mass is 250 times that of Saturn. Its gravity is 300 times stronger than what humans feel on Earth, making it a baby star or protostar. The largest star known in the universe is the red supergiant star Stephenson 2-18 in the Stephenson 2 cluster. Located 19,570 light-years away from Earth, the star was discovered by Charles Bruce Stephenson during infrared observations in 1990. With a diameter of approximately 29,915 billion kilometers, this giant star can accommodate 8 million suns inside it. Although we do not have information about its mass, we know that it emits light with the power of 440,000 suns, making it the brightest star in the universe. In addition to their size, the temperatures of stars in the universe vary. The coldest known star in the universe is a brown dwarf named WISE 1828+2650, discovered in August 2011. The star, located in the Lyra constellation, is approximately 33 light-years away from Earth and has a surface temperature of only 25 degrees Celsius. The hottest star in the universe is WR102 with a surface temperature of 209,727 degrees Celsius. It is among the Wolf-Rayet stars, being 20 times hotter and 300,000 times brighter than the Sun. Located 8480 light-years away from Earth, the star is so hot because it is very close to exploding. Stars become so hot and bright because they start burning heavier elements after depleting their hydrogen fuels, which leads to the formation of a Wolf-Rayet nebula surrounding them. There are billions of stars in the universe with different ages. The oldest star in the universe is believed to be the Methuselah star, which was thought to be 16 billion years old when discovered. Located in the Libra constellation, 190 light-years away from Earth, the star travels at a speed of 1.3 million kilometers per hour. Initially thought to be older than the universe's age of 13.8 billion years, recent research has shown that the star is at most 12 to 13 billion years old. Thus, it has been proven that nothing in the universe can be older than the cosmic microwave background radiation. With mostly hydrogen and helium, and very little iron, the star was formed at a time when iron was scarce in the universe. Additionally, information about its age has become clearer from its consumption of hydrogen fuel and its brightness. The youngest star in the universe is the Neutron star named Swift J1818.0-1607. Estimated to be between 240 and 500 years old, the star was discovered on March 12, 2020, by the Neil Gehrels Swift Observatory belonging to NASA during an X-ray burst. A neutron star is the dense mass of star material that results from the collapse of a massive star into a supernova. With such a dense mass, the mass of this neutron star's material, equivalent to a teaspoon, weighs 4 billion tons on Earth. To put it in perspective, it fits twice the mass of our Sun into a volume smaller than a trillionth. How are star types determined in the universe? Regardless of their temperatures and sizes, star types are determined based on their colors. According to blackbody radiation physics, stars behave like iron pieces heated in a fire. As the iron is heated, it turns from red to orange, yellow, white, and finally blue as the temperature increases. Today, stars are classified using the Morgan-Keenan system. According to this system, stars are classified from hottest to coolest, using the letters O, B, A, F, G, K, and M. Within these classes, they are further divided into subclasses from 0 to 9, from hottest to coolest. For example, A0 represents the hottest, while M9 represents the coolest star. Their brightness, radius, and mass are scaled relative to the Sun's brightness, radius, and mass. For instance, the expression brightness 5 means it is 5 times the Sun's brightness. Let's briefly discuss the types of stars. Blue giants. Referred to as O-type, blue giants are generally hot. They illuminate the surrounding gas and dust clouds, causing them to appear blue. Due to their high temperatures and masses, their lifespans are very short, and their lives end with violent supernova explosions. After the explosion, a neutron star or black hole forms. Yellow dwarfs. Referred to as G-type, yellow dwarfs convert hydrogen into helium in their cores and evolve into red giants as their fuel depletes. Orange dwarfs. Referred to as K-type, they emit low UV radiation, making them the primary focus of the search for extraterrestrial life. Capable of remaining stable for up to 30 billion years, K-type stars, which are 4 times more common than G-type stars, facilitate exoplanet searches. Red dwarfs. These stars are so faint that they cannot be observed without optical support. Due to their low masses, there is little pressure from outside to the center. This allows hydrogen to mix with helium without being under pressure, causing the fusion of hydrogen to helium not only in the core but throughout the star. Thus, the star remains at a constant temperature and brightness for trillions of years. Since the age of the universe is much smaller than this number, no red dwarf has died yet. Giants and supergiants. They form when a star begins to burn helium when its hydrogen fuel runs out. As the star's core collapses and becomes hotter, the heat expands the outer layers of the star outward, turning low and medium mass stars into red giants. However, when stars with masses 10 times greater than the Sun start burning helium, they become red supergiants. In periods of low fusion rates, the star can shrink and become a blue supergiant. This process eventually leads to a supernova explosion. Blue giants. Stars hotter than 10,000 Kelvin, they evolve outside the main sequence. Blue supergiants. They appear before B9 stars. Larger than the Sun but smaller than red supergiants, O-type, and B-type stars turn into blue giants within a few million years when their high masses rapidly deplete their hydrogen and heavy elements are seen on their surfaces. However, some skip the blue supergiant phase and directly evolve into Wolf-Rayet stars. Red giants are divided into 3 types. The most common are RGB branch stars, which convert hydrogen around a stagnant helium core into helium. Red clump stars convert helium into carbon. In AGB stars, helium burning occurs in a layer around a carbon and oxygen core. They have lifespans of up to 2 billion years. Red supergiants. Their outer layers have expanded enormously due to the exhaustion of hydrogen fuel in the core. Although they are the largest volumetrically, they are not the most massive and brightest stars. Red supergiants that create heavy elements explode as Type II supernovae. Additionally, there are dead stars where fusion reactions no longer occur in their cores. White dwarfs. formed when low to medium mass stars shed their outer layers towards the end of their lives, leaving only their cores behind. These stars no longer produce energy, so they resist gravitational pressure through a process called degenerate electron pressure. They can have a mass of up to 1.4 times that of the Sun. Neutron stars. The collapsed cores of massive stars during a supernova explosion, they skip the white dwarf stage. All remaining mass in the star consists of neutrons. They have a gravity 100 trillion times greater than the gravity on the Earth's surface. They resist gravitational pressure with degenerate neutron pressure. However, if the remaining mass of the star is more than 3 times that of the Sun, gravitational collapse continues, resulting in a black hole. Black dwarfs. Stars that are thought to appear after white dwarfs lose all their heat and light. However, white dwarfs live for very long periods, so no black dwarf formation has been observed. Additionally, they are difficult to detect because they do not emit radiation. Black holes. Formed when massive stars lose their outward pressure during a supernova explosion. The remaining mass collapses to a singularity with gravitational force so strong that not even light can escape. Black holes are formed by the supernova explosion of stars approximately 10 times the mass of the Sun. Some galaxies contain supermassive black holes, billions of times more massive than the Sun, at their centers. Don't forget to share your wishes about the stars and the universe in the comments. Don't forget to like and subscribe to our channel for more videos.